Now it's time for the final piece of the puzzle, and that is Gibbs free energy. So just a refresher here, what we're figuring out now is whether or not a particular process or a reaction is thermodynamically favored. An easier way of putting that is, will a reaction occur? As written. And so that means, is it going to happen in the forward direction, or is it going to naturally happen in the backwards direction? And here is the Gibbs free energy equation. So the Gibbs free energy equation is probably one of the most useful equations for this entire unit because it answers for us the question, will a reaction actually occur? And it compiles all the information that we've talked about. If you look in this, you see Gibbs, that's the new guy. You see enthalpy in there, and you see entropy, and there's a little bit of temperature thrown in as well. So to calculate a free energy change, it would be equal to the enthalpy change minus the temperature of the system times the delta S, or the entropy change. Now, something important to note here is all of the units. So Gibbs free energy is in kilojoules, enthalpy is in kilojoules, and when you look in your appendix, or the normal values that are given for delta S are usually in joules. And so you're going to have to change joules into kilojoules every time for this reaction. Also, temperature must be in Kelvin because entropy change is kilojoules per Kelvin. And so your temperature, if it's in Celsius, you have to convert it by adding 273. And let's go ahead and expand that to 273.15 just to give us some more accurate numbers. And just like with the delta H and delta S, with delta G, it's all about the positives and the negatives. And so if the delta G for a reaction, so you plug the numbers in and you get a negative number for delta G, that means the reaction is thermodynamically favored. Another way of putting that is it will occur spontaneously. So a reaction that has a negative delta G would be a spontaneous reaction, which means that it occurs naturally. It doesn't need anything to push it. It spontaneously occurs. So Gibbs is sometimes a little bit hard to process, but let's think about it in terms of water freezing. Now for this process right here, H2O going from a liquid to a solid, that is going to have to release energy, which means that our delta H for this reaction is going to be negative. And the entropy for this, if we think about it in terms of disorder, we're going from a fairly disordered liquid where those molecules are sliding around to a very, very structured and ordered solid. And so that means that our delta S for this reaction is going to be negative because we're going to be decreasing the disorder. Now, not knowing Gibbs and just looking at this information right here, if we were to try and predict whether or not this reaction would occur, it'd be tricky because we know that nature favors exothermic reactions. So we would say, yeah, okay, that's probably spontaneous because it's exothermic. But then we would look at the entropy and we would see that it's negative, so it's increasing order. And we know that nature doesn't favor order, it usually moves towards disorder. And so we'd say, well, no, this reaction would not occur. That's where Gibbs comes in. So Gibbs kind of ties it all together and takes into account, all right, well, if the enthalpy is negative and the delta S is negative, we look at the values of those, we look at the temperature of the system, we can then compare it to the change in enthalpy for G to figure out will it occur or will it not occur. And if delta G is a positive value, that means no, it won't occur. If delta G is a negative value, though, yes, it will occur. So what delta G ends up being then is a certain amount of energy that's built into the system that the system is able to do work, essentially, on its own reaction to get it to occur. So a particular system or reactance has a certain amount of energy kind of built into it, and that's the free energy that can then be used to drive these two processes. So a certain amount of energy that is transferred, that would be our enthalpy, and a certain amount of energy based upon temperature is used to create disorder. And so if there is enough energy from Gibbs to drive both of those processes, we would wind up with a delta G less than 0 or a negative value, which means that we have enough energy for the reaction to occur, and it would be a yes. However, if we have a positive number, that means there's a deficiency, so there's extra energy out here that is not accounted for in the Gibbs free energy, therefore the reaction cannot occur. Here's where it starts getting rocky. So there is two methods for calculating the delta G. The first one is using the equation that we just looked at. However, you're not usually given the delta H and the delta S simply. You have to calculate those first. And we calculate those using the stuff that we talked about in the previous videos. So you would get your delta H using one of the four methods that we talked about before. You'd get your entropy using the entropy values, the standard entropy, and then you could calculate delta G using this method. Or there could be times where you're given delta G and you calculate one of these two, or you calculate a temperature. And then the final way is using the delta G of formation, which is similar to the delta S of formation and delta H of formation. But as a practice example, I'll go ahead and give you the values. So in this case, we have a change in enthalpy of negative 218 kilojoules, and we have a change in entropy of negative 765 joules per Kelvin, and the temperature is 32 degrees Celsius. And the question is asking us, is this reaction thermodynamically favored? Now, it's not asking us for the delta G, but we know that we need to find delta G in order to answer that question. Delta H tells us indo or exo, delta S tells it order or disorder, delta G tells us thermodynamically favored or not. So here's our equation. We'll just go ahead and plug those values in, but we got to make sure that we set the units right. So delta G is going to be equal to our enthalpy, which is negative 218 kilojoules. And we're going to subtract that from the temperature times the change in entropy. Now, temperature is given to us at 32 degrees Celsius. We need to put that over into Kelvin, though. And so that's going to make it 305 Kelvin. And then our entropy, which is in joules, needs to be converted over to kilojoules. And so we're going to have to move that decimal over 3 places so that we wind up with negative 0.765 joules per Kelvin. And if we track our units here, we see that Kelvin is going to cancel out Kelvin, and the units that we're left with are joules. And so that's a good thing because that's the units of delta G, and so we find out that the change in entropy for this particular reaction would be a positive 15.3, which means this reaction would not occur. So this would be a non-spontaneous or not spontaneous reaction. It would not occur. It's not thermodynamically favored. So our enthalpy change and our entropy change, those values are locked in stone with this particular reaction. But what could we change here in order to make this reaction thermodynamically favored? How could we make it so that this number right here becomes negative? Well, the one variable we can change is temperature. So if we change the temperature, we could, in theory, make it so that this number becomes negative. If we think about this mathematically, what's happening right now is we have a negative over here, so we have a negative enthalpy change, and then over on this side we have a negative times a negative, and so this would wind up being a positive value. So our T delta S is positive, and our delta H is negative. And so currently under these conditions at 32 degrees Celsius, our positive value is greater than our negative value, and so we wind up with a positive delta G. If we lower our temperature, though, if we lower the temperature, we're going to wind up with a lower positive number. And if we get that positive number low enough, this number would be higher, the magnitude of this number would be higher, and so we could get a negative delta G. So let's answer the question, at what temperature would that reaction become thermodynamically favored? So currently our delta G is positive, but we want it to be negative. So in order to move from positive to negative, what would occur at that transition point? So there has to be a spot where it goes from positive to negative. And there is. We mark a spot on the number line, and that spot is 0. So at 0 is when it's not actually spontaneous or non-spontaneous. It would be the transition between positive and negative. So where this reaction would become thermodynamically favored would be when delta G equals 0. That marks the exact point where it transitions from non-spontaneous to spontaneous. And we can use the exact same equation here, so that would be equal to delta H minus T delta S. So we're setting delta G as 0, and now we're going to solve for temperature to figure out when this would occur. So just a bit of quick rearranging. Delta H divided by delta S would give us our temperature. Delta H is going to stay the same at 218 kilojoules, and entropy is still going to be negative 0.765 kilojoules per Kelvin. And let's go ahead and cancel out units. We can see that kilojoules cancels out kilojoules, and hey, what do you know? We are left with Kelvin, which is temperature. It's a good sign. It means that the number we get, which is 285 Kelvin, would match up with temperature. So what we found there then is once the temperature reaches 285, so if we were to cool whatever this reaction is down to 285, we would wind up with a spontaneous reaction, so a reaction that is thermodynamically favored. So for whatever this particular reaction is, any temperatures below 285 degrees Kelvin, 285 Kelvin, are going to be spontaneous. Any temperatures above 285 Kelvin are going to be non-spontaneous. All right, so here we can break apart and look at our different delta H, delta S in order to predict whether or not a reaction is thermodynamically favored. Once again, you're not always going to be given numbers. A lot of times you have to look at the information and decide whether or not a particular reaction is thermodynamically favored. So the way you could do this is just by looking at the sign of your enthalpy or entropy. So this is something you can memorize if you choose to do that. But I recommend thinking about it mathematically. Using that kind of processing skills is very, very valuable to science classes and AP chemistry as well. So if we just think about, like this first one, for example, delta H is negative, delta S is positive. Well, if we look up at our equation here, so let's imagine that this number is negative and this number right here is positive. So in this case, then, we have a negative minus a positive. And a negative minus a positive is always going to be a negative value. No matter what the temperature is, we're always going to wind up with a negative delta G. So that means that this is a thermodynamically favored process at all temperatures. Negative delta H, positive delta S, always going to be thermodynamically favored. On the other hand, if we have a positive number for our first one, and then a negative number for our second one, well, in that case, we have a positive minus a negative, and so that becomes positive, and so we wind up with a delta G that's always going to be positive. If it's always positive, that means it's never going to be thermodynamically favored. And it gets a little bit trickier when we have things like a positive positive or a negative negative. So like a positive positive, for example, if you have a positive delta H, right here we would wind up with a negative T delta S, and so this value would have to get fairly high in order to overcome this positive and create a negative delta G. And so that means it'd be thermodynamically favored at what we would call high temperatures and non-thermodynamically favored at low temperatures. So if the temperature is low enough, this positive or this negative number won't be enough to overcome that positive number. So let's take a look at this example, and we're not even going to plug any numbers into this particular equation. We can just look at our values here and say, hey, our delta H is negative and our delta S is positive, and if we look at that equation, delta G equals delta H minus T delta S. Sorry, that's a really bad delta. So that means we have a negative value here and a positive value there. So we're going to have a minus minus a positive, and so that means our delta G has to be negative as well. And so then the answer to this question is yes, this is a thermodynamically favored process. We justified it by showing in this equation that no matter what the temperature is, we're always going to wind up with a negative delta G. Negative delta G always means a thermodynamically favored reaction. And the second method is using the standard standard Gibbs of formation. This is a similar process to what we've done before. So it's the same general equation that we've seen before. The delta G for a particular reaction at standard state conditions is equal to the sum of the balancing coefficients and then the delta G's for the positive. Once again, these values are given for you in appendix number 3 in the back of your textbook, along with the delta H and delta S's. So here's an example problem. This hopefully being something familiar to you because we've used these enthalpy formations or these formations in the back of the book before. Why don't you pause the video, give this one a shot yourself, and resume it, and I'll just put the answer up. Okay, and the Gibbs free energy for this particular reaction is going to be negative 838 kilojoules per mole. So if your number is a little bit different than mine, it might be because my delta G numbers are slightly different. Else, go back and check your numbers. Make sure you balanced by the balancing coefficients and that you use the right states of matter, so not a liquid where it's supposed to be a solid. Now, keep in mind, for these particular reactions, the way you tell if you're going to use the free energy of formation is if you have that little circle in the top. So that means it has to be under standard state conditions. And so it needs to be at 25 degrees Celsius and 1 atmosphere. If it does not meet those conditions, you cannot use those numbers in the back of the book. You're going to have to use a different method to calculate your delta G. And something to keep in mind, that just because a process is thermodynamically favored does not necessarily mean that it's fast. So something that's really thermodynamically favored doesn't mean it occurs really rapidly. Some things like oxidizing is a thermodynamically favored process, metal rusting away. However, it can take a very, very long time for metal to rust, even if it's exposed to all the reactants it needs. In reactions that are not thermodynamically favored, you can force them to be actually occur. So you can drive reactions using electricity or using photons of energy, and that can be used to then convert energy back. So we talk about like photosynthesis, something like this right here. Thermodynamically favored would be the combustion of glucose with oxygen. That would be a negative delta G. That would be a thermodynamically favored process. But if you bring in sunlight, so energy in, you can cause CO2 and H2O to go backwards and form this right here. So you're committing a non-thermodynamically favored process by bringing energy in to drive it. I want to finish up this video just by clarifying a couple terms. So the one that was used interchangeably, and I apologize, is just one of those things, TFP, so thermodynamically favored process, and spontaneity. So a thermodynamically favored process is one that occurs naturally without any outside intervention. That's the same thing as saying a spontaneous process. So I think the textbook refers to those particular reactions as spontaneous. And these would be ones that have a delta G that is negative. Okay, the other one would be your non-TFP reactions. So non-thermodynamically favored processes are the exact same thing as saying a non-spontaneous reaction. So a reaction that will not occur spontaneously, not occur on its own, and those would have a delta G that is positive. And if we think about the thermodynamically favored process idea, a non-spontaneous reaction can become spontaneous just by flipping it around. So something like water, H2O going from a solid to a liquid, melting. When the temperatures are high, that would be a thermodynamically favored process. But if the temperatures are low, if we do this at very low temperatures, that would be a non-spontaneous reaction. Water would never melt at negative 10 degrees Celsius. That means in the forward direction, so that way it would be non-spontaneous. However, if we write it backwards, or just think about it that way, it would be spontaneous in that direction. And this is always true. So any reaction that is non-spontaneous in the forward direction would be spontaneous in the backwards direction. So even though solid H2O would not turn into a liquid at low temperatures, liquid H2O would turn into solid H2O at low temperatures. So any reaction that we write as non-spontaneous can be flipped and made can be made spontaneous, and vice versa. If we have a spontaneous reaction and we flip it, it becomes a non-spontaneous reaction. Where this becomes most obvious is with the activity series. So if we think back to a couple units ago when we talked about the activity series, how some elements can oxidize others while other ones are too weak to do it. And so in this particular reaction, we can see that copper is taking 2 electrons away from 2 silvers or 2 golds to become Au plus and Cu. However, this would be a non-spontaneous reaction. This is not thermodynamically favored. And it's non-spontaneous because copper is not strong enough to take away from silver. However, gold is strong enough to take away from copper. So if we were to write this same reaction backwards, it would become spontaneous. And so as written, this is a non-spontaneous reaction, but backwards it would be spontaneous. So spontaneous in the reverse direction. So we could rewrite this exact same thing as Cu plus 2 Au plus would turn into 2 neutral golds and Cu 2 plus. And so in this top case, our delta G would be a positive value, but in this bottom one, our delta G would be a negative value.